Welcome back to part 2 of sequences and context. This video is we're going to look at a geometric sequence, but before we just call it that, let's read it and see if we can spot it. This is again about Augustus who got candy for doing his homework. And it says, Augustus decides that he needs to be more committed to a healthy lifestyle. He's afraid that all the candy isn't good for him, so he tells his parents that it'd be okay if they just give him 1 candy on the first day, 2 on the second day, and continue doubling that amount each day as he completes his homework. Mr. and Mrs. Gloop like his plan, and they agree to it. Okay, so let's take a minute here to write out this sequence because we can see it appearing right here. Day 1, 1. Day 2, 2. And when they say doubled on the next day, well, that would be a 4, and so on. And I don't know if you spot that right away, but doubling something every day is going to be a geometric because you're multiplying to get to the next term. Right? Doubling is multiplying. So here's our days. Day 1, day 2, day 3, day 4, and so on, right? Well, we know on day 1 he gets 1 piece of candy. Day 2, 2. Then he starts to double it. You get 4, and then 8 is doubling 4, and these are the terms of our sequence, right? Now, if we weren't real sure about this, and I was like, well, is this arithmetic? It seems like some people might say doubling is a constant rate, but it's not, because the distance between these terms is not constant. So 2 minus 1 is 1, 4 minus 2 is 2, 8 minus 4 is 4. This is not a constant rate of change. So what we've just spotted, though, is geometric, because we're doubling. So 8 over 4 is our common ratio. 4 over 2 is 2, 2 over 1 is 2, and so on. All right, so if we wanted to write a formula to predict terms of this sequence, and any questions that are asked of us, an explicit formula is always great. We have the first term times 2 to the n minus 1, and we don't really need that 1 there. I'm just, right, it's 2 to the n minus 1. Okay, does it work? Well, 2 to the 1 minus 1 is 2 to the 0. 2 to the 0 power is equal to 1. Anything, by the way, we're going to talk about this a little bit later, to the 0 power is always 1. So our formula seems to work. Put in 2. 2 to the 2 minus 1 is 2, and it is working. So there's our formula. And it's geometric. And the important part of this is noticing the language of doubling. If it was tripling, it would be multiplying by 3, right? So we know that would also be a geometric. So look for language that involves multiplication. So he did part 3 here. It says model the amount of candy Augustus would get each day that he reaches his goal. Part 4 is going to be a little bit interesting. We want to know what happens, how much candy is he going to have on the 30th day? The number of candies. So we're going to look at f of 30. That's what this model does. It makes predictions. So we're going to say f of 30, and that's equal to 2 to the 30 minus 1, which is 2 to the 29th power. That is a lot of candy. I don't know where his mom and dad are getting all this candy, but let's throw that in this calculator and see what we come up with. So we got 2 raised to the 29th power. It's going to be a big number. Whoa. So that looks like 536,870,912 pieces of candy. Okay. So parents are going to have a tough time finding that amount of candy, I'm pretty sure. 500 million pieces. Does that plan sound feasible? I don't think so, right? I'll write that number on the notes when we get done. So I think that's about it for this video. I wanted to show you a geometric sequence. The next video, I'll show you another one that's a little bit more complicated, but it's also spotting that multiplication, and that's how you spot these geometric sequences. You got to see multiplication. When you see that rate changing by multiplying, it is geometric. All right, I'll see you in the next one.